So, welcome back to this lecture series. In this lecture, we are going to see the conformal mapping and bilinear transformations. Conformal mapping. It is a complex solid function. It is a mapping w equal to f of z from z to z. Okay, that is f is a function from c to c. Is said to be a conformal map at the point z equal to z naught if it preserves the angle between any two oriented curves through the point z equal to z naught in the sense of magnitude and sense. That means in z plane, this is z plane, we have the curve like this. So at this point, it makes an angle theta. Suppose if there is a map f from z plane into the complex plane, f of z is a complex plane, then we'll be having similar curves like this having the angle theta. Okay, that's what the map which preserves the angle between any two oriented curves. What I'm saying, see, we have the complex plane, there are two curves like this, and then it makes angle theta. This is in z plane, and then in w plane we are having similar curves having the same theta. Okay, then if it happens, then we call this as the map as conformal map. Okay, fine. Then the next definition is a critical point. Suppose f of z is a non-constant analytic function, then f dash of z equal to 0. Okay. If any point at which f dash of z equal to 0 means, then such a point is called critical point. The third definition is invariant points of the function f of z. The mapping f of z is said to have the fixed point or invariant points z naught if f of z naught equal to z naught, right? If you solve this equation f of z naught equal to z naught, that gives the invariant point or fixed points, right? So next, let us see some examples related to critical points and fixed points. First example, find the critical points of the map f of z equal to 3z square plus 2. What we want the critical points. So therefore, we have to differentiate this function f of z with respect to z and then equate to 0. So given that f of z equal to 3z square plus 2, then if you do the differentiation, then what is this? f dash of z, that is equal to 6z plus 0. See, therefore f dash of z naught, which is equal to 6z naught. So there is a typo error. This is f dash of z naught. Okay. So f dash of z naught is equal to 6z naught. Then 6z naught equal to 0. See, therefore z naught equal to 0 is a critical point of this function. Next example, find the fixed point or invariant points of the map f of z equal to z square minus 4z plus 6. What is the definition of fixed point? If z equal to z naught is a fixed point, then f of z naught, which is equal to z naught, right? See, therefore, let us call the fixed point as z naught. See, therefore, f of z equal to z square minus 4z plus 6 equal to z. That is z naught square minus 4z naught plus 6 equal to z naught. Then after rearranging this, we are getting z naught square minus 5 z naught plus 6 equal to 0. And then the roots of this quadratic polynomial are the fixed points of this function, right? Then, see, next we are going to see some of the conformal mapping. It is of the form f of z which is equal to z plus a. This is called a translation. It's called a type 1 elementary function, elementary transformation. Type 2 elementary transformation is magnification and rotation. If f of z equal to a z, this is called a magnification as well as rotation. If a is simply a real constant, then it is going to be magnification. If A is a complex constant, then it gives both magnification as well as rotation. Type 3, type 3 transformation is translation, magnification and rotation. That is f of z equal to a z plus b, where a and b are complex numbers. Then type 4 is inversion, that is f of z equal to 1 by z. Now let us see one by one. Type 1 transformation, f of z equal to z plus a, that is a translation. Okay. Now let us consider the transformation f of z equal to z plus a, where a is a complex number, which is of the form a equal to a1 plus ia2, and a1 is a real number, a2 is another real number. Then as I said, f of z, which is a complex function, so therefore it has two parts, that is real part u plus I into imaginary part v. See, therefore f of z can be written as u plus iv equal to f of z, and then z is a complex number, z equal to x plus iy. See, therefore x plus iy plus a is a1 plus ia2. Then you group the real and imaginary part, then you will get x plus a1 plus I into y plus a2. See, therefore if we equate the real and imaginary part, then u equal to x plus a1 and v equal to y plus a2. That is, we have some point, say for example here x plus iy somewhere here, iy somewhere here. In the w plane, it is translated to some other place. Okay, originally it is some here, and then it is translated to somewhere here. Okay, this is what the translation. Then next elementary transformation is magnification function. Suppose if f of z equal to a z and a is a real number, then it is called magnification. If f of z equal to a z and a is a complex number, means then it is magnification as well as rotation. Here I have taken a is a real number, see, therefore it is simply the magnification. Then f of z equal to u plus iv, and which is equal to ax plus iay. See, therefore ax plus iay. If we group the real and imaginary part, then you will have u equal to ax and v equal to ay. Then the third type is translation, magnification and rotation function, that is f of z equal to a z plus b. Here a, b, z both all are complex, right? So a equal to a1 plus ia2 and b equal to b1 plus ib2. See, therefore already we have seen the definition of the complex number through the polar coordinates. So it can be written as a equal to some modulus of a into e power I some theta 1, and b equal to modulus of b to e power I theta 2, where theta 2 is another angle, right? Similarly, z equal to x plus iy, that is equal to modulus of z into e power I theta. Therefore, u plus iv can be written as modulus of a into e power I theta 1 into modulus of z d e power I theta plus b1 plus b2. Okay, b1 plus ib2. Right. Then in the first term, modulus of a into modulus of z are real number, positive real numbers. So therefore we can club this. There is a property, modulus of z1 into modulus of z2, that is equal to modulus of z1 into z2. By using this property, we can club this, right? See, therefore modulus of a is z, and then we are having e power I theta 1 into e power I theta. By using the power law, we can write that is e power I theta 1 into e power I theta. By using power law, e power I into theta 1 plus theta, right? But what is e power I theta? By using the Euler's formula, see, it can be written as cos theta plus theta 1 plus I sin theta plus theta 1. Okay, so that's what we have written like this: modulus of a z into cos of theta plus theta 1 plus b1, because we have the constant b1 here, and then I into modulus of a z sin theta plus theta 1 plus b2. Okay, so what it says that originally the complex number z having the angle theta, if you multiply z by a, then the angle is changed from theta to theta plus theta 1. See, therefore we have some rotation. And then the magnification done by modulus of a z. magnification is done by modulus of az, and then the translation is taken care by b1 and b2, right? See, therefore this function f of z equal to a z plus b represent the translation, magnification, as well as the rotation, right? Then the fourth type is f of z equal to 1 by z. Let us consider the transformation f of z equal to 1 by z. Then u plus iv equal to 1 by z. But z is what? Z equal to x plus iy. Then 1 by z, which is equal to 1 divided by x plus iy. Then you multiply and divide by complex conjugate of this. See, therefore x minus iy divided by x plus iy into x minus iy. That gives x divided by x square plus y square minus I into y divided by x square plus y square, right? So that is our u plus iv equal to this expression. Then after equating the real and imaginary part, we are getting u equal to x by x square plus y square and v equal to minus y by x square plus y square. Or we can write x equal to u divided by x square plus v square and y equal to minus v divided by u square plus v square. Both the way we can write. Now let us see some problems based on this elementary transformation. First example, find the image of the circle. What is the meaning of modulus of z equal to 1? Already we know if z equal to x plus iy, then modulus of z equal to under root x square plus y square. See, therefore modulus of z equal to 1 means under root x square plus y square equal to 1 or x square plus y square equal to 1 square. It is a circle, right? So hereafter modulus of z equal to some a means it is a circle with the center 0, 0 and radius is a. Okay, that is the meaning. So modulus of z equal to 1 means it is a circle with the center 0, 0 and radius is 1. Now we have to find out what is the image of the circle modulus of z equal to 1 under the map 2z plus 1. What is this 2z plus 1? The 2z plus 1 is having magnification and a translation. Why? Because here instead of a we have taken 2, so therefore it gives only the magnification. Right. So what is your f of z? F of z is u plus iv. F of z is u plus iv, that is equal to 2z plus 1, and then z is x plus iy, so therefore we are having 2x plus I 2y plus 1. If you group the real and imaginary terms, then we'll have 2x plus 1, that is equal to 2x plus 1 plus I into 2y. Okay, then if you if you equate the real and imaginary part, then we are having u equal to 2x plus 1 and v equal to 2y. So given the circle, modulus of z equal to 1. See, therefore under root x square plus y square equal to 1, that is x square plus y square equal to 1 square, right? But what is u? U equal to what is u? U equal to 2x plus 1. See, therefore u equal to 2x plus 1. See, therefore we can write 2x which is equal to u minus 1 or x equal to u minus 1 divided by 2. Similarly, v equal to 2y, see, therefore your y which is equal to v by 2. Now we have the circle. What is the circle? X square plus y square equal to 1, and replace x by u minus 1 by 2 and y by v by 2. See, therefore u minus 1 divided by 2 the whole square plus v by 2 the whole square, that is equal to 1. That's what written here. So x square plus y square equal to u minus 1 divided by 2 the whole square plus v by 2 the whole square equal to 1, right? Okay, what it says, there is a common factor, common denominator, you just multiply this equation by 4, so therefore u minus 1 the whole square plus v square equal to 4. So modulus of z equal to 1 is a circle It is a modulus of 1 equal to 1 is a circle. So wait a minute. So modulus of z equal to 1 is a circle in the complex plane. That means it is a circle here. Now we are getting another equation. This is here, this is x-axis and this is y-axis. Now we are having another equation in w plane. Let me call this as u-axis and this is v-axis. So what it says? This says it is a circle with the center 1, 0 and radius is 2. So circle with the center 1, 0. This is 1 and 0, right? This point is 1, 0 and having the radius 2. See, therefore we'll be having the circle with the center 1, 0 and radius is this, like this. Okay, look at this. We are having a unit circle here, whereas here the circle with the center 1, 0 and radius is 2. Radius is 2, that is magnified. Right. And then the origin of this circle is translated to the another point 1, 0. So therefore the translation happened and then the magnification is also happened. Right. Now let us see the next problem. Find the image of the strip 1 less than x less than 2 under the inversion map f of z equal to 1 by z. What does it mean? 1 less than x less than 2 means x is a bounded variable, that is x can vary from 1 to 2, whereas y can vary from minus infinity to plus infinity. See, therefore in a complex plane, x, this is your x-axis and this is your y-axis. X is bounded by 1 and 2, whereas y from minus infinity to plus infinity. See, therefore this is your 1 and this is your 2. Then the strip means the region bounded by these two vertical lines. So this is your strip 1 less than x less than 2. Now we are going to find out the image of this vertical strip under the transformation f of z equal to 1 by z. Right. So what is f of z? That is u plus iv. 1 by z means this is x divided by x square plus y square minus I into y divided by x square plus y square. If we equate the real and imaginary part, we are having u equal to x divided by x square plus y square and v equal to minus y divided by x square plus y square, or x equal to u divided by u square plus v square and y equal to minus v divided by u square plus v square, right? As like the previous problem. Now the strip having the relation 1 less than x less than 2, it can be written as 1 less than x and x less than 2. So 1 less than x can also be written like this, that is x greater than 1. 1 less than x or x greater than 1. Both are same, right? So let us assume each one has one case, that is 1 less than x or x greater than 1. Okay, let us assume the first case. Right, x equal to u divided by u square plus v square, which is greater than 1, by using this relation. Why? Because here x equal to what? X equal to here u divided by u square plus v square, and then which is greater than 1, see, therefore u divided by u square plus v square, which is greater than 1. Now you cross multiply this by u square plus v square, then you will have u greater than u square plus v square. Okay, then we can write u square plus v square minus u. Why? Just a minute, let me erase this. So here u greater than u square plus v square, you can also write like this, that is u square plus v square less than v. If you subtract this, we'll get u square plus v square minus v less than 0. Okay, that's what this equation. Okay, right. Then u square minus u plus v square can also be written as u square. You just multiply and divide by 2 in order to make the perfect square like this. Right? We have minus u. Here you multiply and divide by 2. That is u square minus 2 into 1 by 2. 2 into 1 by 2, that gives 1 plus v square. Nothing is changed, right? We are multiplying and dividing it by 2. So the equation is same. That is u square minus 2 into 1 by 2 u. Then you add and subtract 1 by 4. Add and subtract 1 by 4. Now look at this. If we take this bracketed term or boxed term, that is of the form u square or a square minus 2ab plus b square, right? A square minus 2ab plus b square. In order to make the perfect square, we are doing such a add and subtract and multiply divide by some suitable constants, right? Nothing else. So u square minus 2 into 1 by 2 u plus 1 by 4, that is nothing but what? U minus 1 by 2 the whole square, right? U minus 1 by 2 the whole square plus v square. We have another minus 1 by 4. You just pull this minus 1 by 4 to the right hand side. Okay. Okay, then see, therefore your u square minus u plus v square equal to u square minus 1 by 2 minus 2 into 1 by 2 u plus 1 by 4 minus 1 by 4 plus v square less than 0. See, therefore you just push this minus 1 by 4 to the right hand side. See, therefore the sign will be changed. So the remaining is u square minus 2 1 by 2 u plus 1 by 4 plus v square less than 1 by 4, right? So by using the second formula, we can write u minus 1 by 2 the whole square plus v square, which is actually this is less than, okay, less than 1 by 2 the whole square. U minus 1 by 2 the whole square plus v square, which is strictly less than 1 by 2. What does it mean? X minus a the whole square plus y minus b the whole square equal to r square means it is a circle with the center a comma a and radius r. But x square, okay, this is a meaning, right? Now, if you are having less than r square means it is inside the circle. If you are having x minus a the whole square plus y minus b the whole square greater than r square means it is outside the circle. Okay, I repeat. Just a minute. X minus a the whole square plus y minus b the whole square equal to r square, which is on the circle, and then x minus a the whole square plus y minus b the whole square strictly less than r square means inside the circle, with the center a comma a and radius is r, and x minus a the whole square plus y minus b the whole square greater than r square means outside the circle, with the center a comma b and radius is r, right? So from these notes we come to know that u minus 1 by 2 the whole square plus b square strictly less than 1 by 2 the whole square means it is inside the circle with the center 1 by 2 comma 0 and radius is 1 by 2, right? So the first relation 1 less than x says that inside the circle with the center 1 by 2 comma 0 and radius is 1 by 2. Now we have another case, x is less than 2. Okay, now let us see the next case. If x less than 1 by 2, sorry, x less than 2, but x is what? X is u upon u square plus v square. You multiply this by u square plus v square, then you will have, what is this? U less than 2u square plus 2v square or u square plus v square minus u by 2 greater than 0, right? We have this expression, that is u square minus u by 2 plus v square. You just multiply and divide by 2, that is u square minus 2 into 1 by 2 into u by 2 plus v square. I just multiplied and divide by 2 here in order to make the perfect square. So that is equal to u square minus 2 into 1 by 4 u, 2 into 1 by 4 u, and then I added and subtracted some constant in order to make the perfect square. How I got this number? Whatever the number we are having the coefficient as a coefficient of 2u, then you take the square of that number. In the previous case, what happened? In the previous case here, we have simply u, then 2 into 1 by 2, right? 2 into 1 by 2. While adding and subtracting some constant, you take this number and take its square and then add and subtract. Okay, what is the square of 1 by 2? That is 1 by 4, right? You added and subtracted here. In a similar way, we have 1 by 4 here. See, therefore take the square and then add and subtract. That is 1 by 16 minus 1 by 16, right? So nothing is changed, right? We add and subtract, see, therefore nothing will be changed. Here you multiply by 2 and divide by 2, see, therefore nothing will be changed, right? Now u square minus u by 2 plus v square equal to u square minus 2 into 1 by 4 plus 1 by 16 minus 1 by 16 plus v square greater than 0, right? We have the constant minus 1 by 16. You just push this number to the right hand side. See, therefore we'll have u square minus 2 into 1 by 4 u plus 1 by 16 plus v square, which is strictly greater than 1 by 16. Okay, now by using the above second hint, we are rewriting the first 3 terms as u minus 1 by 4 the whole square plus v square, which is strictly greater than 1 by 4 whole square, right? Already we have seen x minus a the whole square plus y minus b the whole square, which is strictly greater than r square, means outside the circle. Okay, see, therefore what it says, this equation says that the region outside the circle u minus 1 by 4 the whole square plus v square, which is strictly greater than 1 by 4 the whole square, that is outside the circle with the center 1 by 4 comma 0 and radius is 1 by 4, right? So now we are going to find out the region, right? So what is given to us in z plane? In z plane, see, this is your x axis and this is your y axis. The vertical strip, this is x equal to 1 and this is x equal to 2. Okay, the region bounded by these two vertical line. Okay, see, this is your vertical strip. Now in w plane, the first circle is inside the circle with the center 1 by 2 comma 0 and radius is 1 by 2, right? Inside the circle with the center, see, this is your u axis and this is your v axis, and this is 1, this is 2, this is 3 and this is 0, right? So what it says, inside the circle with the center 1 by 2 and radius 1 by 2. Okay, let me elongate this because otherwise it is very difficult to draw this. Okay, let me read scaling this. So this is 1 by 4, 1 by 2, 3 by 4, then 1. Okay, right. So the first circle says that inside the circle with the center 1 by 2 comma 0. So first draw the circle with the center 1 by 2 comma 0. This point is 1 by 2 comma 0, right? See, therefore, draw the circle with the center 1 by 2 comma 0. See, therefore, the circle will be like this. Or is there any possibility to? Yes, yes. The circle is this one. Okay, circle, right. So inside this bigger circle. Then this equation says is outside the circle with the center 1 by 4 comma 1 by 4 comma 0 with the radius 1 by 4. So we have to draw the another circle with the center just a minute. So with the center 1 by 4 comma 0 and radius is 1 by 4. Okay. See, therefore the intersection of these two region is outside the black color circle and inside the red color circle, that region, right? So this is your a required region under the map f of z equal to 1 by z. Okay, clear? Is it clear? Right. Okay, then so next let us see the bilinear transformation. Bilinear means it is linear with respect to both the variable, right? So the transformation w which is equal to a z plus b upon c z plus d, where a, b, c, d are the complex numbers having the relation ad minus bc is not equal to 0, is called the bilinear transformation. Okay, that is f of z equal to a z plus b upon c z plus d, provided ad minus bc is not equal to 0, is called bilinear transformation. That means it is linear with respect to both the variable. Linear with respect to both the variable means linear in w and linear in z, right? Now next definition, cross ratio. The cross ratio of four numbers z1, z2, z3, z4 is defined as z1 minus z2 into z3 minus z4 divided by z1 minus z4 into z3 minus z2. Okay, it is very useful formula when we compute the bilinear transformation, right? Just to remember this. Now there is a theorem, what it says, the bilinear transformation that maps the points z1, z2, z3 from z plane onto w1, w2, w3 in the w plane is given by the map w minus w1 into w2 minus w3 upon w minus w3 into w2 minus w1, which is equal to z minus z1 into z2 minus z3 upon z minus z3 into z2 minus z1. Okay. So what it says, exactly these points z1 will be mapped to w1, z2 will be mapped to w2, z3 will be mapped to w3. That means if I take this is my function f of z, that is f of z1 which is equal to w1 and f of z2 that is equal to w2 and f of z3 that is equal to w3. Exactly it will map to these 3 points. Under the map this f of z equal to a z plus b divided by c z plus d, right? This cross ratio which brings the function like this a z plus b divided by c z plus d. That is the advantage of this cross ratio. Let us see one or two examples related to the bilinear transformation. Find the bilinear transformation that mapping the points z equal to 1i minus 1 onto w equal to 2i minus 2. Okay. Now there are 3 points in z plane are given. Similarly, There are 3 points in W plane are given. Now by using the previous theorem, see, we are having the formula W minus W1 into W2 minus W3 divided by W minus W3 into W2 minus W1 equal to Z minus Z1 into Z2 minus Z3 divided by Z minus Z3 into Z2 minus Z1. Now given that Z1 equal to 1 and Z2 equal to I, Z3 equal to minus 1 and W1 equal to 2, W2 equal to I and W3 equal to minus 2. Replace all these values in the formula. Then you just cross multiply, then group the terms, then you rewrite W in terms of Z in the form AZ plus B divided by CZ plus D. Right? That is a required bilinear transformation. Okay, very simple. You just identify what is Z1, Z2, Z3 and W1, W2, W3 and replace those values in the formula and then group the terms and rewrite W in terms of Z in such a way that W equal to AZ plus B divided by CZ plus D. That is a required bilinear transformation. Right. Then see next problem. Find the bilinear transformation that maps the points z equal to 0, 1, infinity from the extended complex number, okay, into w equal to I, 1 minus I. Suppose in any places, if you are having infinity, then we have to redefine our formula in a simple algebraic calculation. We'll see it now. Find the bilinear transformation that maps the point z1, z2, z3 from z plane onto the w1, w1, w2, w3 from w plane given by this formula. But z3 is infinity, okay? z3 equal to infinity, which implies 1 by z3 equal to 0. So we cannot deal with the infinity. See, therefore, if you are having infinity in n places, then we have to redefine. Instead of that variable, you just put that as 1 by that variable. That gives 0. So w minus w1 into w2 minus w3 divided by w minus w3 into w2 minus w1. But z3 is infinity. See, therefore, you take it common. See, therefore, what it gives? W minus I into 1 plus I and w plus I into 1 minus I. I have taken z3 common. See, therefore, z minus z1 into z2 divided by z3 minus 1, right? Here also in the denominator also z3 into z divided by z3 minus 1 into z2 minus z1. Now we can cancel this variable z3, right? Now we apply the limit, that is replace z3 equal to infinity. Then what will happen? This will become 0 and this will become 0. The only thing is w minus I into 1 plus I divided by w plus I into 1 minus I, that is equal to z minus 0, and 0 minus 1 divided by 0 minus 1 into 1 minus 0. After simplification, you will have the nice formula w equal to z plus I upon 1 plus zi. Okay, that is a required bilinear transformation, right? In a similar way, suppose if w2 equal to infinity means, then we have to redefine your formula. Instead of w2, you have to use 1 by w2, okay? 1 by w2, right? Okay, thank you.